So entropy, this is one of the more abstract concepts that we're going to deal with, but you'll oftentimes hear that entropy is a measure of the disorder of a system. And we use a symbol S for entropy, and the units are joules per degree Kelvin. Entropy and the second law of thermodynamics are really important for understanding why certain processes are reversible, why other processes are not reversible, and how different things affect the overall efficiency of a system. Now, we've already seen that with reversible processes, we have the highest amount of efficiency, whereas when we have a heat engine or heat pump with irreversible processes, the efficiency goes down. And again, a few different people who worked with the second law of thermodynamics included Rudolf Clausius, and his ideas became sort of the basis for understanding this concept of entropy. And again, we try to think of entropy as a measure of disorder in a system, but entropy is better in terms of how irreversible a system is. So let's take a look at the case of a glass that's being shattered. We start out on the left-hand side, and we have, a case of low entropy. There is order to the glass, there's no defects, basically it's intact. As more and more fractures occur, the entropy increases until finally we have nothing left but a whole bunch of shards of glass in our high entropy state. Now, what is the difference between the photograph on the left and the photograph on the right, or the images from left to right? Well, this process is irreversible. So whereas we can go from left to right in this diagram, we certainly can't go from right to left. Yeah, you could put all the pieces together and reforge it, or remelt it and recast it, but that's not going back and going to the original low entropy state. You're using external processes to go there. But again, we can take this glass, hit it with a hammer, and go to our high entropy state, but there's really nothing we can do to do the reverse, okay? So in many ways, entropy can be looked at how irreversible a process is. It also is very much connected with the arrow of time, that as time goes by, the entropy of different systems tends to increase, and that's part of the second law of thermodynamics. So let's look at some cases of increasing entropy. Most combustion reactions are increasing entropy, okay? Again, it's very easy to combine oxygen with some fuel and ignite it and combust it, and we get the release of heat and carbon dioxide and water vapor. However, going the other way is difficult. How do we resynthesize, the original fuel? I mean, if it's hydrogen and oxygen, we can, of course, use electricity to break the hydrogen and oxygen up from the water. But for most of the taking a hydrocarbon and combusting it, it's an increase in entropy. It'd be very difficult to turn the carbon dioxide back into fuel. We can do it, but the process in doing that would actually be a high entropy process. Metabolism of living objects, that is a case of increasing entropy. As we age, our entropy goes higher. Our sun will be only around for 5 billion more years, at least in its current state. As hydrogen is converted into helium, that is an increasing entropy process. And again, the universe eventually will grind down to a halt. So again, the change in entropy is can be defined for any process, surprisingly, by taking the heat absorbed by a particular system and dividing it by the temperature at which it's absorbed. Actually, it's a little more complicated than that. I think it's ds equals dq over t, but we'll keep it for a constant temperature. This process happens at a constant temperature. Then we can use this equation here, which is a little bit easier than the differential form of it. Okay. So let's do an example, and we'll show how entropy increases for an irreversible process. Here we have a hot reservoir. Oops, let me get rid of that. I thought I had my pen going. At some TH of 1000 degrees Kelvin. And then we're going to allow heat to flow into a cold reservoir at 300 degrees Kelvin. Okay, so let me take a chunk of this heat and I'm going to let it flow into the cold reservoir. Okay, it's at 1000 degrees Kelvin. I'm going to remove the heat, so it's going to be negative. So negative 1000 joules divided by 1000 degrees Kelvin corresponds to a change in entropy of negative 1 joule per Kelvin. Okay, so that's my change in entropy. All right. Now, for my cold reservoir, now, first of all, you're like, well, look, delta S is less than 0. Doesn't that, go against the second law of thermodynamics? We're not done yet. We're connected to the cold reservoir. Now the cold reservoir, we are accepting this 1000 joules at 300 degrees Kelvin. So that's a change in entropy of 3.3. So I lose entropy up here in the hot reservoir, and I gain entropy in the lower reservoir. I lose 1, I gain 3.3, and the net change in entropy is 2.3 joules per Kelvin. Okay, so clearly what we can see here, this is an irreversible process. This is heat flowing from a hot reservoir to a cold reservoir, and that corresponds to an increase in entropy of the system and an increase in entropy of the universe. Now, for reversible processes, we've already stated that reversible processes don't really exist. But we use a Carnot engine because we know that consists of reversible processes. And in this particular case, if I had a perfect Carnot engine, I could take the heat from the hot reservoir. It's still negative 100 joules per degree Kelvin. A Carnot engine has a maximum efficiency between 1000 degrees Kelvin and 300 degrees Kelvin of 0.6. So, yeah, I did the math incorrectly. Well, in any case, let me do a little edit right there. So 3/10, of course, is 0.3. That should be 0.7. Okay, so I'll have 700 joules instead. And roughly 700 joules of work going out of here. And then, yes, 300 joules being dumped down here. Sorry about that. I needed to make that little little edit right there. 700 plus 300 gives me my 1000. So 1000 comes out of the hot reservoir. Of that, 700 goes into work. Only 300 gets dumped into the cold reservoir. Well, we take a look at this and we see that my hot reservoir lost 1 joule per Kelvin. My cold reservoir gained 1 joule per Kelvin. And what's interesting about this is if I could reverse this Carnot engine and turn it into a Carnot refrigerator, I could put that work back in and get that 1000 joules to jump back where it started out. So this would be a completely reversible process. And we know that as it is completely reversible, delta S is equal to 0. Okay? Now remember, the second law of thermodynamics says delta S has to be greater than or equal to 0. So the best we can hope for is a reversible process where delta S is equal to 0. Okay, so irreversible process, entropy increases. Totally reversible processes doesn't exist. Again, that's 700. Entropy change is 0. Okay, so again, it sort of shows the arrow of time. Let's say I've got a bunch of molecules on this side, nothing here. Okay, I can open this divider right here, and what happens? It equalizes. Okay, what's happened to the entropy? Well, we've gone from a system of order, molecules on this side, no molecules on this side, to somewhat disorder where the molecules are now all over the place. Again, this gas has expanded irreversibly because I can't just simply move this piston back where it was. I would have to do work on the gas and recompress it. Okay, that would take energy from the outside. That would indicate entropy increasing on the outside. So again, second law of thermodynamics, reversibility, the characteristic of a process which would allow the process to occur in the precise reverse order. Again, as long as the process is completely reversible, there's no increase in entropy. However, when it's irreversible, entropy will increase. There's no process that's possible where the sole result is the removal of heat from a low temperature reservoir and the absorption of an equal amount of heat in the high temperature reservoir. Why? Because delta S in that case would be less than 0. Even though we don't defy conservation of energy, the best we can do according to the second law of thermodynamics is that S is greater than or equal to, delta S is greater than or equal to 0, okay? And this violates that. So that is a big no-no, as we said before, when we first introduced the Clausius statement. Kelvin-Planck statement, no process is possible where heat is removed from a single reservoir without an equivalent amount of work being produced. Again, big problem here. Delta S would be less than 0 in this particular case, because then I could take the work back and pump even more heat from the cold reservoir to the hot reservoir, even if my heat pump were not a completely reversible process. So once again, that's not allowed. All of these ideas are connected to the second law of thermodynamics, that overall no thermodynamic cycle can have a thermal efficiency of 100%, okay? No thermodynamic cycle can result in a decrease of entropy in the system, all right? Okay, quick review. First law of thermodynamics, conservation of energy, that's no big deal. We've always had that since physics 1. But again, second law, even when we conserve energy, we have to limit the direction where the process can go forward, okay? It's all connected to entropy, okay? Okay, definition. Entropy is a theoretical measure of the thermal energy that cannot be transformed, So it cannot be used to create work in a thermodynamic system. So the higher the entropy goes, the less available energy we have. So entropy is like, how bummed you are, how much lazy energy you have. It's the unavailability of energy or the reversibility of a process. In all real processes, entropy never decreases. Entropy in the universe is always rising, okay? So, we said, well, if it's a reversible process, delta S is equal to 0. Then we said, there's no real reversible processes. So now we get to the conclusion, well, in actuality, anytime anything happens, entropy is going to increase, okay? And certainly, we can't have a decrease in entropy. Cannot do that. That is not allowed. Delta S can never decrease in a closed system, okay? So a good example of entropy in an ordered system would be a stack of dominoes. You knock one down, you get this chain reaction, they all start falling down. But again, imagine that if you put one domino up, all the other dominoes aren't going to suddenly go up again. Okay, we've gone from a state of low entropy, where they're all ordered and standard upright, to a state of high entropy. Okay, so a state variable related to the second law of thermodynamics is entropy. Entropy, entropy, entropy. That's what we're always watching. Let Q be the energy absorbed or expelled during a reversible process at constant temperature. Then again, we can calculate the entropy of the system, the change in entropy of the system, as being QR over T. Okay, as long as T is constant. Okay, so this would work for an isothermal system. We could calculate the change in entropy. And there it is. Okay. Again, this is only good for T as a constant. For adiabatic processes, we'd have to use something like, and I hate to do this because I keep saying, oh, it's another calculus course. ds is equal to dq over dt. Okay. All right. When entropy is absorbed, when energy is absorbed, Q is positive and the entropy increases. That's why the cold reservoir increased its entropy. When energy is expelled, Q is negative and entropy decreases. The hot reservoir always decreased its entropy, but because it was a coupled system, even when the hot reservoir decreased its entropy, the cold reservoir at least increased its entropy by the same amount, or increased it even more for the irreversible process. The entropy of the universe increases in all natural processes. We've said that. Nuclear fusion, that is an increase in entropy. Just about every thermodynamic process has some increase in entropy because nothing's perfectly reversible. And again, we can think about it this way. The second law of thermodynamics does not allow for perpetual motion machines. We always have some friction in any mechanical system. There's some friction, some turbulence, some viscosity, and that's going to rob the system of some of its energy. And it's going to turn that energy into heat, okay? That increases the entropy. So really, we can't have a mechanical system that keeps moving forever, okay? As time goes by, that friction is robbing it of energy and essentially increasing the entropy of that system and the universe. Again, sometimes entropy can be described in terms of disorder. I like to think of it as, much closer to the concept of entropy is a measure of how much energy is unavailable to do work. That's the best way about thinking about it. That you can have a system with tons of energy, okay, tons of energy. For instance, you can have a hot reservoir and you can have a cold reservoir. And as long as they're two different temperatures, we can get work to go into a heat engine, okay? And then, heat to go into a heat engine, and then to be the excess heat to be dumped to the cold reservoir. But as soon as these two reach thermodynamic equilibrium, okay? Oops, that's not what I wanted. As soon as these two reach thermodynamic equilibrium, okay? No more heat's going to flow, okay? Even though we might have started out with a tremendous amount of energy, once we reach equilibrium, there can be no transfer of energy. There can be no generation of work, even though the energy hasn't gone any place. The energy is still there, okay? Okay, if you want to go into even more detail in terms of entropy, there's actually an equation for not just the change in entropy, but the actual entropy of a system. And the total entropy of a system is equal to this, and this is a little hard to understand. This is the Boltzmann constant right here. The Boltzmann constant you can look up. The Boltzmann constant is important for a lot of things in thermodynamics. But here is the really tough thing to understand. The natural log of the number of proportional possible states. Okay. Generally, one way of thinking about thermodynamics is systems tend to evolve to a more probable state, okay? So that's why what we oftentimes will see is a system going from lower entropy, okay? We're at a low entropy state. What does that mean? It means that initially starts at a less probable state to a higher entropy state where it's more probable that the system will be like that. Like before, we used the example of, oh, we have this container of gas, it's got a little partition right here, and we have all the molecules on one side, and then we open up the partition and all the molecules flow to the other side. Okay, what's the most probable state here? Well, as long as that partition is in, nothing's going to change. But once I remove that, it's much more likely that all the molecules will distribute evenly on both sides. What is the chance that, oh, suddenly all the molecules, okay, I got to erase this, all the molecules, oh gosh, I lost the whole thing. What's the probability, here I go, that all the molecules are going to return to their original state, that all the molecules are going to go, oh, I'm tired, I'm just going to go off to the left and fill this side up and leave the right side unfilled. Now, yes, the molecules could all of a sudden end up on the left side by pure chance. When you're talking about like Avogadro's number of molecules in a mole of gas, the probability of that is so low, it's not going to happen. Okay? So what does the system tend to do? It tends to go to the state of increasing entropy, increasing likelihood that all the molecules will smooth out and be on both sides. Okay, let's use a pair of dice to illustrate this. Everybody's used dice, right? You probably played Monopoly at some point in your life, or Yahtzee, or one of these things, okay? Hopefully you're not gambling, you're not playing craps. But in any case, if you look at the possibility of rolling different numbers, like if you roll 2 ones, the sum of the two is going to be 2. If you roll a 1 and a 2, the sum will be 3. You roll a 1 and 3, or 2 and 2 is 4. If you know anything about dice, the most probable number that you can roll is 7. Why? Because there are 6 possible combinations that will lead to the number 7. Okay? So a 7 is so much more probable than rolling a 2. A 2 is possible, but not really probable. Okay? So we can look at the entropy of each of these states. Now, again, this is just 2 different particles. Okay? So there can be random fluctuations between the 2. When, again, you're talking about Avogadro's number, 6.022 times 10 to the 23rd molecules, the probability that they will all end up in a particular state is very, very highly unlikely. Okay? So looking at the entropy, let's calculate the entropy for each different case. The entropy for rolling the 7 is, here's the Boltzmann constant. It's 1.38 times 10 to the minus 23 joules per Kelvin. there are 6 possible states, so we take the natural log of 6, and the result is an entropy of 2.47 times 10 to the minus 23. Okay, so that's the entropy. Remember that, 2.47 times 10 to the minus 23. Now let's do the entropy for rolling A2. Well, that's easy. The natural log in natural log S, what power of E do we have? Well, anything to the 0 is 1, so the natural log of 1 is 0. The entropy for coming up with a 2 is 0. Okay, 0 joules per degree Kelvin. So if I start with 2s and I roll it, my chances are I'll probably end up with a 7, a 5, an 8, a 9, or a 4, but it'll be very unlikely that I will roll snake eyes, 2 times in a row. Okay. So again, real systems, we're dealing with massive numbers of particles. So it's like taking 6.022 times 10 to the 23 die and rolling them and having them all come up 1. It's not going to happen. Okay, you won't get that degree of order. Okay, there's only one combination that gives you that. And again, consider 2 boxes of particles of 2 different gases. The reds are on the left, the greens are on the right. I don't know, maybe we have nitrogen and oxygen, here, and all the O2s over here, and all the nitrogens here, right? Okay. How likely is that going to happen in the room? Okay. Are there different parts of the room where you're like, oh yeah, I love this. There's oxygen here. I can breathe here. And other parts of the room are like, I better move to the other side of the room because there's no oxygen. It's all nitrogen. It doesn't happen, folks. It mixes nearly evenly because that's a higher entropy state. Okay. That's a more probable state. So if I separate the gas where I've got oxygen on one side and nitrogen on the other side, what's it going to do? It's going to progress to the higher entropy state. Okay. All right. So again, we can look at this another way. We can say grades of energy. It's a tendency of nature to move toward a state of disorder. Disorder, I'd like to say higher probability. It affects the system's ability to do work. Okay. Heat tends to flow to cold. So what's going to happen? The more probable state, or the state at which something is going to evolve to, is thermodynamic equilibrium. Okay. And again, not all energy is equal. Okay. For instance, chemical energy such as is contained in hydrogen and oxygen, you combine those two and they go boom, right? I can get work out of that. I can do combustion. I can use hydrocarbons, and that's a carbohydrate. I can use hydrocarbons and combine them with oxygen, right? I know. Let me put methane here. And I can get energy and I can run, some thermodynamics, some heat engine with that. I'm not going to balance this equation. I don't have to take chemistry anymore. But that chemical energy is a higher grade of energy because I can do something with that. Okay. If instead I have heat, okay, just heat sitting there, unless I have a hot reservoir and a cold reservoir where the heat can go someplace, I'm not going to be able to do anything with that heat. Okay. All right. Let's say the heat is, distributed evenly all over the room. What am I going to do with that? It's still energy. It's energy just like the chemical energy. But if it's not organized where we have 1 part hot, 1 part cold, that heat's just sitting there, I'm not going to be able to do anything with that. And that's where entropy is really, really important. It tells you a lot about of the energy that you have, what you can do with it. Okay. As we said, heat death of the universe, the entropy of the universe is always increasing. One of the big places where we're getting entropy increasing is hydrogen is being converted into helium in stars. Okay. Eventually, when we don't have any hydrogen left, no more stars. Yes, helium can be converted into other things like carbon, oxygen, so on and so forth, when they're giant stars or they're supergiant stars. But that nuclear energy, which is available right now for stars, it's eventually going to run out. These stars are going to go dark. What happens then? Well, we still have gravitational energy. But as more and more matter falls into black holes, less and less energy will be available to do work. Okay? We think that at some point, the universe is just going to wind down. There'll be no more available energy to do anything. And that'll be the case where nothing is left but the residual heat that we've dumped in from some hot reservoir as the universe reaches thermodynamic equilibrium. The shortest part of this course, the shortest part of this chapter, sorry. The third law of thermodynamics. What is the third law? The second law is a little bit hard to understand because it says that entropy is always increasing, or at least not, is either the change in entropy is equal to zero or it's increasing. The third law of thermodynamics is concerned with absolute zero. The third law of thermodynamics states the entropy of a system goes to zero as the temperature goes to zero. Okay, what does this mean? Yeah, again, entropy goes to zero as T goes to zero. What this means is when we run a refrigerator, as we cool it down, it'll take more and more energy to get closer to absolute zero. Okay, let me show this to you. All right, we're at 300 degrees Kelvin. We want to cool to 0 degrees Kelvin. This is not exactly true because there's other nuances here. But let's say I want to cool down to 150 degrees Kelvin. Got my little refrigerator here, and I cool down to 150 degrees Kelvin. Let's also say that it's going to take me 1,000 joules of work to get down there. Okay, fair enough. Will it take me 1,000 joules of work to go the other 150? Not so simple. Okay. To get to 75 joule K, using the same process and oversimplifying everything, it would take me another 1,000 joules. Okay. To get to, it's half of 75. Oh, trying to do this in my head. 37.5. Let's get to 37.5. It'd take another 1,000 joules. Okay. See what's happening here? As we're getting closer and closer to absolute zero, it's taking me progressively more and more energy. Remember that coefficient of performance? I said that as things get colder, the coefficient of performance goes down. Well, yeah, it's harder and harder to extract more and more energy as I get closer and closer to zero. In fact, the closest that we've gone to is, I think, a few nanokelvin. And it takes a tremendous amount of energy to get there. But again, the amount of energy would need to be infinite to reach absolute zero. And that's a consequence of the fact that entropy goes to zero as temperature goes to zero. All right. All right. I think they actually got a little bit lower than this. The lowest temperature ever achieved using laser cooling brought sodium potassium vapor down to about 500 degrees Kelvin, 500 nanokelvin. That's 5 times 10 to the minus 7 Kelvin. Temperatures as low as 1 picokelvin are predicted possible if we do this in a non-gravitational state. So we can get real close, but the third law of thermodynamics says you ain't never getting to 0 degrees Kelvin. Okay, you will never be able to remove all the thermal energy. Okay.